Na kuzebe kama laure.
Okay, so the first question, David, can we see the screen?
Yes, Prof, I can see.
All right, okay. Guys, if there's anything that you want to say while we are going on, feel quite free to put it in the chat column. If there's something that you don't understand or you make a contribution, don't feel shy. Just put it in the chat column and we will address it at the end of the session. Okay, so let's have a look at the very first question. The midpoint M of AB is joined to the third vertex of triangle ABC so that these three are equal. MA equals MC equals MB. Generally, the midpoint of AB will just be these two equal, but now we are given in addition that the distance to C is also the same, right, as these two. So the question is, we are asked to calculate angle ACB. It's angle C, in other words. This angle here, this entire angle. Now, very often, in geometry, you may be surprised to know that we can use algebra. In fact, I am very fond of using algebra in geometry questions, by which I mean that unknowns, I can give symbols to them, x's and y's and so on. I know people are in the habit of writing angle ACB and so on, right? I'm not very fond of this. If it's necessary, then we will do it, but otherwise, I will just call this kind of an angle, I just give it a name. I'll call it X. Like in this case, I think I'm going to call this particular angle, no, it's ACM. Okay, let's ignore that. So we call them X's and Y's and then try to get equations and then try to solve, all right? So in this case, we need to calculate angle ACB, but no angles are given at all. But what we can see in this picture are two isosceles triangles, right? Because you got MA equals MC. So this triangle MAC is isosceles. Now, you know that in an isosceles triangle, if the two sides are equal, then the angles opposite the sides are equal, also equal. So this angle, which is opposite that stroke, is equal to this angle, which is opposite that stroke, and we are looking at the left-hand triangle. So let's give a name. Let's call this X here. As we said, we'll give a name to this because we know that these two angles are the same. Right, so we can put XX. So it's very easy way. Instead of writing angle MCA equals angle MAC, this is what the textbooks do. Right? But it's too complicated to look at it like this. Now you can actually see which angles we're talking about without having to, track these symbols. All right. Now, and of course, if you do write it like that, then you have to give a reason. And the reason is that MC is equal to MA. Maybe that's one of the reasons why they use this complicated notation, because you can't say X equals X. So you have to say exactly which angle you're referring to. So maybe we can write it like this, and then we can say X equals like that. And the reason in brackets is that MC equals MA. That's why these angles are equal. You must give a reason because they give you a mark for that and they give you a mark for that. If you don't give a reason, you lose a mark. Okay, likewise, in this triangle here, you've got, this is also isosceles, and you've got MC equals MB. So therefore, this angles opposite these equal sides here are equal. And again, you can write the same thing down. And this time, the reason will be MC equals MB. to get that extra mark. Okay, now you've got 4 angles, but if you look again, you will see that those 4 angles, they take care of all the angles in the triangle. And you know that the sum of the angles of a triangle is 180 degrees. So that's very useful because now we can start adding all these 3 angles. This angle here is x plus y. This angle is x, this angle is y. So we have that x plus y plus x plus y. And those are the 3 angles of the large triangle. That we know is 180 degrees. And if you want to give a reason, you will say angles of a triangle. Because that's quite sufficient. The sum of the angles of a triangle is 180 degrees. So that will be the reason. In geometry, you must always give a reason. Right? Everything must be justified. And you either use a theorem, like this is a theorem here, and this is also a theorem, or you can use something that is given, a given information, in which case you'll put given. Like if you wrote down MC equals MB, MC equals MB, you could have said it's the reason why MC is equal to MB is because it is given. See? So you could have put down MC equals MB given. Right. So you use the given information in geometry and you'll use the theorems in geometry to prove results in geometry. Okay. So the reasons can be given like this. And sometimes you need not be theorems, but it could be reasons for congruency. Also, and then that reason you'll have to give in brackets. It could be side, 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 or side angle, side, or whatever the reasons of congruency. Now let's get back to this here. This thing now simplifies to 2x plus 2y is equal to 180 degrees. Now the algebra kicks in. 2 into x plus y is 180 degrees. So 2 times x plus y is 180 degrees. So x plus y must be 90 degrees. But x plus y is precisely this angle here. X plus y, if you look at the picture, it's angle ACB. If you add these 2 angles, you can get this large angle ACB, and that's precisely what you need to calculate. So it's a very interesting problem that this angle here is 90 degrees. So whenever you have a situation like this, the angle is 90 degrees. Now, so let's just have a look at this and say, well, what's the conclusion? This picture here allows you to say that this angle here is 90 degrees. So whenever you have this kind of a picture, the angle is 90 degrees. We can, if you think about that, we can say a little bit more. Because I can draw a circle with this as center, and all these become radii. Let me see if this is right now. One of these, select, which one is it? Yeah, it's this one. So we could select this thing. But I just want to move this and see whether it fits in. But no, it's not big enough. Okay, I need to make it a little bit bigger. I don't know where the center is. Let's draw another circle. Oh man. Okay, let's just draw that one. Sorry, all this is a mess, but I can clean it up. I know how to do it. Well, hopefully this will fit inside. Oh, it's gone too big. Anyway, oh, maybe it's, yeah, right. I can make it a little bit smaller. Even smaller. All right, see, the point is now, if you put your compass at M and you take this as your radius, you can draw a circle because this, all these 3 points, are all at the same distance from M. So if you draw a circle with your compass, right, then these point B, if this is your radius, which is defined by your compass, it must go through C, it must go through A because all these 3 are equal. But then if you look at this, it means that what we've got here is a circle, and because M is the center, and you've got a line going through the center, that's a chord. A chord is a line segment that joins any 2 points of a on the circumference. So this is a chord, and the AC is also a chord, BC is also a chord because you're joining 2 points on the circumference. But this chord is very special because it goes through the center, and that's called the diameter. So AB is the diameter. We have to say is a diameter because there are many diameters, all straight lines which go through the center. Right? So what we are saying here is that if AB is the diameter of a circle, then when you take a point on the circumference and you join that point to the endpoints of the diameter, the angle that you're going to get is 90 degrees. So that is what we have proven here. So that's a very important fact. So if I remove all the other things here, and just draw another circle, so what we are saying here is that if you draw any circle and you draw a diameter, it must go through the center. Let's make it look like this. Imagine the center is there, and we have just drawn it through the center. So that point is the center somewhere. Then if I take any point on the circumference, and start from one end of the diameter, go up to that point, come down to the other end, then you have this setup here. Because this is the center of the circle, because this equals this, because they are radii. Radius of a circle, that's the thing about a circle, that every point on the circumference, its distance from the center is the same. That's why it's a circle. So you got these 3 are equal, which is the same thing. And we just proved that this angle here will have to be 90 degrees. So this is an important theorem in mathematics, that if you have a circle and if you have a diameter, then you can, this angle that is formed like this is always a right angle, 90 degrees. See? Doesn't matter where the point is. Like that, this angle here will always be 90 degrees. Very interesting result in geometry. So let's remember that. That is what we have proved here. Okay, so let's get on to the next one. I took some time there because there were some interesting observations regarding that particular problem. Okay, let's just clear all the drawings. So the second problem with the diagram, ABDE is a square. So the outside thing is a square. Okay. And the triangle EFD, this big triangle here, is equilateral. So we've got these two facts here. And also you got that FC equals FB. I've got it written down here. FC equals FB. All right, let's just write down all this information. Well, as far as possible, you always write all the information that is given in the diagram. Now, all these are equal, but I don't want to put a single stroke here because I got a single stroke here. I don't want to confuse these two, so I'll put a double stroke here. So all these are equal. The four sides of the triangle are equal, of this square. And of course, we also know that the angles are 90 degrees. So we'll just put that in reserve. But this triangle is equilateral. And this side here is double stroke. So all the sides of this triangle are equal. So I have to put double stroke here because one of them is double stroke and all of them will be double stroke. So all the information that is given, that ABD is a square and EFD is equilateral, I'll put it in here. The only thing I haven't used so far is the right angle for the square. Okay, now what is the question? The question is find angle DFC. DFC. So this is the question mark is here now. So how do you find that angle? Okay, now the angles of an equilateral triangle are all 60 degrees. Hope you know that. An equilateral triangle, the sides are all equal and the angles are all 60 degrees. If you don't know why, then it's very easy to prove because in an equilateral triangle, it's also isosceles. So these two are equal. So therefore, from what we said earlier on, if this is x, so is this. So these two sides are equal and therefore the angles opposite them are equal. But now if you use the fact that these two are equal, right? So you have you have an isosceles triangle facing that way, and therefore the angles opposite those sides are equal. X is already here, so therefore this angle here will have to be x, because these two are equal. But now you have in your original triangle, you have all the angles are equal. Right? And you also know that in any triangle, when you add up all the angles, you're going to get 180 degrees. So you have the 3x is x plus x plus x, that's 3x, the sum of the angles of a triangle. You can put the reason down here, sum of the angles of a triangle. And if 3x is 180, then 1x is 60 degrees. So that is why all the angles of an equilateral triangle are 60 degrees. You can actually prove it because you use the fact that it's an isosceles triangle in two different ways. Okay, so we need to calculate that question mark there. So let's just write down this information that you got here so far. Namely, that these angles here are 60 degrees. So I can put down 60 degrees here. 60, 60, 60. All right, so what else do we have? Can we proceed from here? Well, we can, because this whole angle here is 90 degrees, and we got that this is 60. I'm focusing on this side here because I want to try to get to this angle here. So this angle is part of this triangle here, you see, FCD. So immediately, because this whole angle is 90 degrees, this one here has to be 30 degrees. Right? Because these two angles, they add up to 90 degrees. One of them is 60. So at least now we got one angle in this triangle. If we know another angle, then we can work out that one. So we are nearly there. Now, where do we proceed from here? Well, if you look at this picture carefully, you'll see that DF equals DB. Right? Because DF is a side of the equilateral triangle. It's equal to ED, because all the sides of the equal triangle are equal. Actually, you can put in brackets DF is equal to ED, because this is an equilateral triangle, and ED is equal to DB, because this is a square. So therefore, you can start with DF, and you can conclude that it's equal to DB. So, but that makes that an isosceles triangle. So therefore, these two angles, angle DFB, the angles opposite it, are equal. So this is an isosceles triangle. The angle, I'm saying FBD. So you have to focus on this triangle, which is sort of upside down. But the angle of the side, angle opposite this equal side is that one. That's what I wrote down here, DFB. See? And this angle opposite this one in this triangle here, which you know to be isosceles, is FBD or DBF. So that's why this is true. Now, you got these two angles are the same, and they all add up to the 30 degrees plus these two equal numbers add up to 180 degrees. Okay. So therefore, if this is 30 degrees, those two angles sum to some 150 degrees. These two equal numbers, which we just saw, add up to 150 degrees because this whole triangle is equilateral. I'm not writing everything down. So you have to listen carefully. So, because the sum of the angles of a triangle are 180 degrees. So this 30, those two add up to 150, but they're equal. You see, it's very important. And two equal numbers adding up to 150 means that each of them must be 75. You will be very careful of that. A lot of people in geometry, they say, if you add two numbers and the answer is 10, they say it's 5 and 5. Can't be. Unless you know they are equal, then you can say that. But if you don't know they are equal, they are up to 10, anything goes. 2 plus 8, 3 plus 7, 1 plus 9. But if they're equal, straight away you know what they are. So now we can write down that this angle here is, we can put a 75 here. Right? And then now we are inside the small triangle here. And now we are given that these two are equal. So you have an isosceles triangle sitting inside here. And one of the angles, the angle opposite the single stroke here is 75. So for the angle opposite this single stroke on this side will be 75 also. Okay, now you got two angles in the small triangle. The angles are 75 and 75, so that's 150. And therefore, this angle here will be 30. BFC. I'm not writing anything down. I'm just saying all these things, and you can learn how to write them down and give reasons, as I showed you. But I'm going to leave that to you. So you've got these two are equal because these two sides are equal, and they add up to 150 degrees. Everything, all three angles add up to 180. So the remaining angle will be 30 degrees. And now we can get to our question mark, because what we didn't use is that angle DFB this guy here is 75 degrees. DFB is 75, and one piece of that is 30, so the other one must be 45. Because these two add up to 75, and we just calculated this to be 30. And so we solved the problem because we needed to work out what the question mark is. So answer, the angle DFC, 45 degrees. So this is a very good application of isosceles triangles. And in grade 9, 8, and 9, especially grade 9, when you're introduced to geometry, that's one of the big things, one of the big facts about isosceles triangles. If the angles are equal, then the sides opposite those equal angles are equal and conversely. Okay, so we use this thing several times here, right? That fact eventually to get to the answer. All right, so this is a very nice problem. Now, let's get on to the next problem. I don't know about you, but I like geometry because geometry is so logical. But the important thing is you must know whenever you say make a statement, you need to give a reason. You need to justify. You need to be accountable. And if you don't do that, then it just becomes a guess. And the whoever is reading it will want to know, why are you saying this? Right? The reason is very important. So you have to say, if you say something which is true, they'll give you a mark for it. They will assume that you know the reason, but you forgot it. So they'll give you the benefit of the doubt. But if you wrote a correct thing down, and you also give the reason in brackets, then you get full marks. Otherwise, you only get 50% of the marks. So that's very important. How to write this thing down, and in brackets, you must give the reason. And even the reason too, like you might have to say it's given, you know. There are lots of reasons. If you say alternate angles, you must say the lines are parallel. You must say these lines are parallel. Or these parallel, and if you need to say why they are parallel, you can say it's because it's given, you know. So from the given, you build up, from the theorems, you build up to get newer and newer results. And that's why geometry is so interesting. Because from some bare facts, you can make conclusions and eventually come to whatever you are required to prove or required to calculate. Like in this case, we're required to calculate something. So you got AB is the diameter of a circle. So you got AB. We just spoke about diameters. So this is AB, and you got a circle here. And CD is parallel to AB. CD is parallel to AB. So let's just put that down. The diagram will show it. It's parallel. Right. Now MC, this is MC, it meets AD at the point E. Actually, the word meters, you should say cuts. So this MC, it cuts AD. It doesn't meet it like a T junction. So you got CM will meet AB at M. That's fine. It meets it here. But now we are going right through, so you have to say cuts. Anyway, it's not important for the problem, but I just thought I might mention it. Now, and AC equals EC. AC equals EC. So I'm going to put down these two are equal. So you've got a small little isosceles triangle sitting here. AC is equal to EC. And therefore, you can conclude that these two angles are equal. But we'll just hold on with that. Now, they say find angle CAM. CAM. Question mark. CA, this whole angle here. Now, what makes this problem very fascinating is that not a single angle is given. And yet you're asked to calculate some angle. People will say, no, this is impossible. They forgot. They didn't tell us what at least one angle so that we can calculate. And they just carried on like this. And then they're asking us to prove something. The remarkable thing is that even without that information, you can still calculate this angle CM, and we will see how. All right, now you got a circle. So that means that all the radii are equal, which means you're going to get lots of isosceles triangles, right? And you also have another isosceles triangle. So once more, you've got a problem involving isosceles triangles. And you've got parallel lines, which means we can use things like alternate angles are equal, corresponding angles are equal, co-interior angles are supplementary. Those are the important facts about parallel lines. Alternate angles are equal, corresponding angles are equal, and the co-interior angles, they add up to 180 degrees, or otherwise they are supplementary. Now, the thing about this problem here is that, okay, I can see one pair of angles equal because I got this parallel, this line, transversal, parallel line. You got a Z, because you got parallel lines, you see. Then you can say talk about Z's, and these are alternate angles. So let's give a name to this. Let's call this angle X. That one. And that is going to be equal to this angle here. And the reason for that is, I'm not writing everything down. The reason for that is they're alternate angles. Right. Now, if you continue like this X here would be equal to another angle, but it's not mentioned yet. Because there's an isosceles triangle here. I'm going to actually draw that isosceles triangle. You see, MAD, and we know that MA is equal to, M is the center of the circle, you see. So this is the radius. And all these radii are equal. So I could join this thing. I'm using red to show that that line wasn't there, but we just drew it in. That's what we call a construction. So I've actually made a construction here because I think it's going to help me. Right, come on. Now, I want this thing to be open now to everybody. David, you can give all of them access. And please put your hands up if you can tell me which other angle is equal. If there are any other conclusions you can make from this. We made one conclusion that the alternate angles are equal. Is there any conclusion anybody can say? Don't be shy. Just put your hands up. Dutuko, did you want to say something? Darak? Can you name any other angle here in this picture? Suhrit? Oh, we got one chat there. Okay, that's good. Let's see who's saying what. Oh, Darak is saying that MAD equals MDC because triangle MDA is isosceles triangle. Okay, let's see what Darak is saying. MAD is equal to MD. Derek, are you saying this? I think you are saying this. You're saying these two angles here are equal. Because you say MAD is isosceles. That's quite correct. Now these are equal here. I'm going to put double stroke with the radii. Those two are radii. And I can put another stroke here as well. So these are all radii. And there's another one. This one here, MC, is also double stroke. Okay, so I'm sure we're going to use that. Okay, now, so now we've actually got 3 x's here. Is there any other angle that we can name? You can put it into the chat column the way Derek did it. I'll give you a hint. We've got an isosceles triangle here, MD equals MC. All right, no one? So this angle here is 2x now, because the angle opposite MC is 2x, and MC equals MD. So this is isosceles here. If that is 2x, this is 2x also. Okay, now can anybody tell me any other angle in this picture? Come on, the quicker you answer, the faster we will go. Okay, so I'm assuming that you can't tell me. But you see, these are parallel lines here. So when you come here and you go down and go this way, you got a Z like that. And so therefore, this angle here is 2x. The other Z angle. Talking about this angle here. So that angle is 2x. Yeah, very interesting, because you can still proceed. You see, now I just want to point out to you that in this triangle here, AEM, the small baby triangle here, I've got 2 angles. One is x and the other is 2x. So I can calculate the third angle. How do I do that? I add these two, x plus 2x, which is 3x. And I can say that the third angle is 180 minus 3x, because you have to add these two angles and subtract it from 180 to get the third angle. But you don't really have to go to the third angle. You can also use exterior angles. See? Because if you look at this picture here, you've got this situation here. I'm going to put C. This is CM. And then I'm going to go up to that, to A. And go to that. I've got a flag now, you see. I mentioned in some other time about the flag. And the angle we are looking at this. This is C, this is M, and this is A. I'm just looking at this one here, C, M, and this is E here. C, E, M, A. And we have that this is X, and this is 2X. So with the exterior angle theorem, this is 3X. Now this angle here is the sum of the 2 interior opposite angles. So it means that this angle here, which is exterior to this triangle, that's 3x. Okay, so, but now we are in the small triangle here, and we know that this is isosceles. So if this is 3x, this is also 3x. Because these two are the same. Now, there is another isosceles triangle here which is not easy to see, and that is MC equals MA also, you see, because these are radii. MC equals MA. So you got another isosceles triangle, namely MAC. So MC is equal to MA. And you got one of the angles is 4x because there's 3x plus x. So the angle opposite MC is 4x. So therefore, MC equals MA. So this angle will also be 4x. So now you've got every angle in this picture here is known. You've got x, you've got 2x, you've got 3x, you've got 4x. Very interesting problem. All in terms of x. But now finally we got an equation because we've got that this whole angle here, which is 6x, plus this whole angle here, 4x, these are co-interior angles. The one which I've got a curl here and this double curl. So these are co-interior angles, and co-interior angles are supplementary. So when you add those two, you're going to get 180 degrees. So you finally got an equation. We had to work our way to the problem to come to the equation to see what's equal. And we finally got it because we're using the fact that co-interior angles are supplementary. So you got 10x is 180. So x is 18 degrees. So we actually calculated what this x is. We didn't know what it was, but we actually calculated it, which is quite remarkable because we weren't given any angles whatsoever. But that wasn't the problem. The problem was to find CAM. So angle CAM. That's what we needed to find. But now CAM is easy to see because you got a 3x there, you got an x there, so it's 4x. It's 3x plus x. So this angle here is 4x, but we know what x is. So this is 4 times 18, and that is 72 degrees. In fact, you can calculate all the angles here because everything is in terms of x. Wherever you see x, you put 18 degrees, and you can get 2x or 3x or 4x, and so on. So this is the solution to this problem. We used isosceles triangles several times. So the problem which I'm just giving you is all about isosceles triangles. And I've chosen interesting problems because these are some of the more challenging problems with isosceles triangles. And they're quite remarkable. That's what I like. In this case here, not a single angle is given, yet you can calculate all the angles, which is very remarkable. Okay, so now we want to go on to the next problem. Oh, I think I had an alternate way of solving the problem, but it's a little bit more complicated. I could have used the fact that AB is a diameter. And earlier on, we said that if you got a diameter and if you got a point on the circumference, there's a certain angle which is 90 degrees. Right? We could have done that. But in that case, we would have had to join DB and then angle ADB is 90 degrees. You can try that. I think it's a good exercise to work on, to using the fact that this is a diameter and using the fact that that's 90 degrees, you might still be able to come to the conclusion that that angle X is 18 degrees. Okay, let's get on to the next problem. So if you read this thing, it says the vertices of triangle ABC. I usually get somebody to read these things out, but you guys are not very cooperative. So far, only one person answered the many questions that I've been asking. So I have to answer all my questions myself. And I'll even read it myself. The vertices of triangle ABC are the centers of three circles. Okay, as you can see, you got a triangle and the vertices A, B, and C. A is the center of that circle, B is the center of that circle. So we know these are centers, which means that from the center to the boundary, all these lines are equal in length. They're all called the radius. Right? That's the thing about a circle. All right, if A, B, and these circles, they just touch each other. So you can see this circle is just sort of touching this one is touching this, and these are supposed to be touching also. But I didn't draw it too accurately. They're actually supposed to be touching like that. Now, they also say AB is 3 inches. So the interesting thing about two touching circles is that when you join the centers, they will go through the touching point. So it's an interesting fact. When you got two touching circles, or you call them tangential circles, which touch a certain point, then if you join the two centers, it will contain that common point. Right? And the circle they're touching, there's one point which is common to both of them. Sometimes you call it the point of contact. Right? So the point of contact lies on this line here. That's a very important fact. So here too, this is a straight line, and this is a straight line going through these contact points. All right, now they've got AB is equal to 3. So this length here is 3, and AC is equal to 4. That's A to C. Determine the sum of the diameters of the 3 circles. Now you got 3 circles, therefore you got 3 diameters. Therefore 3 radii. So let's give names, as I told you, as I've been telling you so far, to those unknown quantities, and give symbols to their names. Okay, so like for instance, I could call this radius here, I can call it A, right? The distance from here to here. And maybe this radius here, I can call it C. Small c, not capital C. Capital C represents the center of the circle. So I'm allowed to use a small c. So small c represents the radius of circle C. Sometimes you speak about a circle, instead of saying circle with center C, sometimes they say the circle C, which it's not, it's not ambiguous. We'll know exactly which circle we're talking about. And then also the radius of the circle, we can call it B. Okay, so now we need to know the sum of the diameters of the three circles. So the diameter of circle A is 2A because A is the radius. The diameter is twice the radius, right? That's the diameter of one circle. The diameter of the second circle is 2B. The diameter of the third circle is 2C. So we need to know that one. Determine the sum, right? We're adding of the diameters, got the three diameters of the three circles. So what is that quantity equal to? Now we got some equations here. We got that, for instance, you see this is B here. So we can say this part here is also B. The radii, and here to the radius is C. So from here to here is also C. That's the distance from the center to the boundary. In a circle, the distance from the center to the boundary is always the same. That's what's called the radius. Okay, now we've got some equations here because we are told that, oh, we got BC is also equal to 5. Right, so what have we got? Let's write down the equations. Here, this is also A here. Goes from here to here. So if you look at this length here, this A plus B is equal to 3. Because the distance from A to B is A plus B, and this is given that the length is 3. So likewise, this part here, if you cast your attention to that part, you will have that A plus C is equal to 4. And if you take this part here, your B plus C is equal to 5. So the sides are A, 3, 4, and 5. Now we want 2A, 2B, 2C. This bit of examination will tell you that, look, I got two A's here, I got two B's here, I got two C's here. So if I add all these things up, I'm going to get 2A plus 2B plus 2C. And that on the right-hand side is 12. And that's answered the question. See, if you write down what you require to find out, it helps you a great deal because they said some of the diameters, you have to translate that into symbols. And we know the radii are A, B, and C. So therefore the diameters are 2A, 2B, and 2C, right? The radius, the diameter is always twice the radius. So exactly twice. So we need to work out the sum of those. And then once we write the three equations, the sum just throws itself out. Because you can just see that on the left-hand side, you got two A's, two B's, and two C's. So after that, it becomes quite trivial. All right. So in this problem here, you've got some kind of a tiling. Nothing is said about the tiling, but I think we can assume that all of them are squares. In the actual question, they would have said it, but I just copied it down like that. So all these small squares, and you join a couple of vertices, and the angle between those two lines is equal to x, and they ask us to calculate x. Okay. So where do we start here now? Very little information is given. Now I have to say this is quite a advanced problem. And see, it's problem number 13, which is close to 15. So it is probably one of the team competition problems. And they are usually quite hard. Okay, so let's see what can we do here? Where can we start? As it stands, I can't do much. I've got that this diagonal here is a diagonal of a 3x1 rectangle. Just observe that. And this diagonal here is a diagonal of a 2x1 rectangle. And these rectangles are made up of squares. Okay. Now, the way to do this is actually to draw a construction. I had to try many times before I eventually decided on the right construction. And the construction that we have to do is this one. That wasn't there. Or maybe that's not the construction. Let me just yeah, I think it is though. Yeah, right. No. Yeah, the one that I want to draw is this one. Yeah, that one. Now, the reason why I draw that one is that this here is a diagonal of a 2x1 rectangle. And this one here is also the diagonal, this one, of a 2x1 rectangle. So we can see that they must be the same, they must be equal, right? Because they both are diagonals of the same rectangle, the same two rectangles have got the same sides. So these two are equal. And that line there is also equal to that. And one interesting fact about quadrilaterals, right? And this is done in grade 9, maybe in grade 10, is that if you got a quadrilateral whose opposite sides are equal, any quadrilateral whose opposite sides are equal, suppose you got this equals this and that equals that, then you can conclude that this whole quadrilateral is a parallelogram. That's a crux. But anyway, even if you don't know the theorem, you can easily guess that this is a parallelogram. You can see that this part is equal to this part, and these two are equal. And this is already parallel. All these lines are parallel. So this is parallel, and you can kind of see that this must be parallel. All right? Okay, so now you got that. So where do you go from there? Now, if you look at this picture here, you can see I've got an X here. And if you just look at, if I just repeat that, and I repeat the X here, and I repeat the other line here, this is there, this is there, that is X. Then you can see that you got corresponding angles. This angle here will be X, because you got an F here, there, coming down, another one down there. So you got F angles, and F angles are corresponding angles. So that is X. Right, now to proceed with this thing here, we need to calculate. So now we need to calculate that X. So how do you do that? Well, to do that, you have to perform another construction. Like that. So why do we perform this construction? Well, again, this is also a diagonal of a 2x1 rectangle, because if I produce this thing here, I'm going to get a rectangle this way. It wasn't there, but this rectangle wasn't there, but you can see this is going to be the diagonal of a 2x1 rectangle, and therefore this is also a diagonal of a 2x1 rectangle, so they must be equal. All right, so these two are equal. Both of them are diagonals of 2x1 rectangles. Now there's another thing here. You see this, if I call this dot, this angle here, this angle is an angle in this triangle. That one, that one, that one. And this is a 2x1 triangle, not a rectangle. 2x1 triangle. In this picture, you got another 2x1 triangle. 2x1 triangle, and it's a right angle triangle. So these two triangles are congruent because you got a right angle and you got two sides, and you got a side and you got the hypotenuse equal. So you use that fact about hypotenuse, side, and angle. So these two triangles are congruent. In other words, they are identical in every respect. So if this angle is a dot, so is this angle. Now, why am I doing all that? I'm doing all that because I know where I'm going to. I need to calculate this angle here, you see. What is that angle? One part of that is dot, right? Now, you know that dot plus this part is 90 degrees. If we call this, if we just call this curl, well, I don't want to use x's and y's here. There are too many angles, and it'll just clutter up the things. So if I call this angle here curl, you can see if you look at this triangle here, dot plus curl is 90 degrees. And therefore, dot plus curl here is 90 degrees. So these two angles are 90 degrees, this angle. Now you can look at this triangle here. If you want, you can call it ABC. We know that in triangle ABC, angle A is 90 degrees. We just proved it, it's dot plus curl. And you got AB equals AC, you see, because they are diagonals of rectangles. Or if you like, because these two triangles are congruent. That's another reason. We just showed these two triangles are congruent. So therefore, this must be equal to that. And therefore, you got an isosceles triangle. The sum of these two angles, yeah, so therefore this whole angle here is x, because this equals that. And the third angle is 90 degrees, so therefore x plus 90 is 180. So we have to prove that this is 90 first. Then you can say we know all the three angles. And if you work it out now, you got 2x is equal to 90. And x is the angle that you try to calculate. It's 45 degrees. It's a long way to get from this point here to where we were. It's the power of geometry. See, but we have to draw some lines and all that to get to the answer. So we have to perform two constructions. To join some lines and then use congruence to hit the problem on the head. It's a difficult problem, I admit. Okay, so the next problem is this assignment problem. Okay, so this is the assignment problem. So the geometry problem again is involved isosceles triangles and so on, and I'd like you to try it and submit your answers. Right, it's an interesting problem, but the kind of problems we have done today fits in very well with this assignment problem. So I don't think you should have any problems. Okay, so and then we get on to the next problem. Oh, now we've abandoned geometry. Now we've got some logical problems. So you got 11 stroke 5. It means that I'm looking at lesson 11. We only went up to lesson 9 because we had less time. But I've chosen a problem from session 11, which was supposed to be originally session 11. And I'll put that problem in here for you to work out as an assignment. A bag contains 65 marbles of the same size. So you got a bag and you got all these marbles. And there are 65 of them, and they're all of the same size. Right. And 20 of them are green. 20 of the marbles are green. Or I should have started with red. 20 are red. 20 red, and 20 of them are blue. The nice thing about this computer kind of stuff, you can actually show the colors. Okay, now I'm recording the information on my paper. Lindiva removes marbles from the bag without looking. Now, because they're all of the same size, she can't distinguish between them. And she's not looking at it, so she doesn't know what the colors are. The question is, what is the smallest number of marbles she must remove to ensure that she has 10 of the same color? Now, you might argue, well, the smallest number is 10 because she takes, puts her hand and by chance, all 10 are green, in which case they are of the same color. Right? But that is not what they want. What the question is asking for is, that's very specific. You're not looking now. It says without looking. You could have drawn 3 red. Oh, there's more to it. 5 are either yellow or white. Oh, there are 5 which are yellow or white. A little bit more. Okay. So when she's just looking, she draws 10 marbles. She could have taken 3 blue. Oh, Let's just get to another color. Yellow is not a very nice color to take. She could have had 3 blue, and then she could have had 2 red, or she could have had 4 blue, 4 green, and she could have had 1 white. She was looking. That makes up 10. But that doesn't satisfy the condition. She wants 10 of them to be. Oh, but she's removing. She keeps removing them. So she could have, if she came to this, so that's fine. Or she could have done, and this is 10. This gives you 10 things. But she could have had 5 red, and then 11 green, and then she lands with 10. No, not 11 green, 9 green, and then 10 blue. She could have come to this situation. In this case, she'll make 24 draws. And she's guaranteed, not guaranteed, she has 10 of the same color. Now the question is, you want to guarantee that you have 10 of the same color to ensure, right? You want to guarantee that. So you have to consider the cases where this doesn't, the worst possible case, be a total pessimist and say, well, if the thing is really bad, then what you could have done is the following. She could have withdrawn after a certain time. She looks at the coins in her hand. She sees that she's got 9 green, 9 red, 9 blue, and she has all the whole lot of these things. She has all of them. 5 yellow stroke W, yellow and white. Now she could have had this. This is the worst situation, because she got 9 green, but she's not getting the next 10th one. She's got 9 red, she's not getting the 10th. And similarly with the blue. And of course, she goes all the other stuff which she doesn't really need, because she can't get a pair from that or 10. But in this case, situation here, the moment she draws one other, the only ones that remain are, all these have been taken out. The only ones that remain are 11 green, 11 red, and 11 blue. That's what she's left with. In the bag. But the moment she puts her hand in the bag, she's going to take out either a green or a red or a blue, and then she's got the 10 that she's wanted. So this is a critical. This is the critical stage. And after this, she needs one more to guarantee that she's got 10 of the same color. So the answer is, she draws 27 plus 5, which is 32. Right? But we still haven't got 10 of the same color. But now, this is the tip of the iceberg. There's one more will clinch the deal. 33 removals. So when she takes 33, she can be assured that there are 10 of the same color, because the worst possible case is that one. All right, so that is your problem there. It's I'm sure you might have been able to solve that. Got enough confidence that you would have been. And then the next one is this one. Now it's all logic now. It's not so much. We're not doing any more geometry. Okay, you got 5 circles overlap in 9 regions. So you got these 5 circles which look like the Olympiad insignia, I think. They overlap like this. Now you want to place one of the numbers from 1 to 9 without repetition in each region. So you want to put, you could have had a 1 here, and 2 here, and 3 here, and 4 there, and 5 there, and 6 there, and 7 there, and 8 there. Now it's already filled. 8 here, 9 here. Right? And that could have been a possible way of filling these 9 numbers so that there's no repetition. But now that sum of the numbers in each circle is 11. Now this doesn't work. The 4 plus 9 is 13. So this is not what you're looking for. In every circle, the number must be 11. So now that's quite a challenge. How do you put these numbers into these circles so that you can get so that you get your solution? Now I know many of you guys are very good in this. You'll try this and try that, and eventually you'll get to the answers. You can use some kind of a logic, and then you'll say, okay, I need to put this number there or put that number there, right? But there is a proper way of calculating this thing. You might be fascinated to know that it's actually possible to determine what these numbers are by pure logic. All right, so let's look at our information again. What we've got is that all these numbers, A plus B is 11, B plus C plus D is 11, D plus E plus F is 11. So all these add up to 11, right? And we also know that the numbers from 1 to 9 are spaced in between. Nothing is repeated. So we can use that first fact to say the sum of all the numbers since none of them are repeated, and there are 9 numbers, by the way, yeah? 1, 2, 3, 4, 5, 6, 7, 8, 9. So the 9 numbers fill in those things. So if you add up all the numbers there, it's 1 plus 2 plus 3. And when you add up all these, you get 45. I would do it like this. 1 plus 9 is 10, 2 plus 8 is 10, 3 plus 7 is 10, 4 plus 6 is 10. So I got 4 tens, 40 plus 5 is 45. Right. So if you add up all these numbers, you get 45. Now, the other thing about this is that each circle has got 11. It adds up to 11. So the sum of all the 5 circles is equal to 5 times 11. And that's 55. In other words, you have those 2 add up to 11, those 2 add up to 11, those 2 add up to 11. But if you add up, don't worry about what's inside there. 11 plus 11 plus 11 plus 11 plus 11. You get 55, but that's more than 45. And if you ask yourself, why is it more? And the answer is that because you're counting some numbers twice. So which numbers are you counting twice? The only numbers you're counting twice is that one. You got A plus B and you got B plus C. Actually, you got B plus C plus D. So that's counted twice. And the same thing here. This is counted twice. And here too, you're counting it twice. Right? You would have counted F plus G plus H. and you got E plus D plus F, and then this H. Also, you're counting twice. You count it in this circle, count it in this circle. Right. So, what's the conclusion? So the only numbers which are repeated are B, D, F, and H. Those are F and H. So these numbers, because they are each is counted twice, then they are the ones which are contributing to the 55. So originally it was 45, but suddenly you land up with 55. Where is the extra coming from? It's coming from these numbers which are counted twice. So if you add up what do you get? You get 10. Because you get 45 if you don't count them twice. And then now if you add those 4, then you're counting, you are calculating the sum of all the numbers in the 5 circles. So it has to be 45 plus 10. So now you say, hey, but wait a minute, you got four numbers which are adding up to 10. There's only one way in which 4 numbers can add up to 10. And those 4 numbers will have to be 1, 2, 3, 4. Those 4 numbers. Right. The smallest, they're all different. So these are the 4 smallest numbers are at the intersection. 1, 2, 3, 4. But you don't know where they are. I could have 1 and 2, and I could have 1 and 3, and 4 and 1. We don't know how they are spaced. So we still need to answer that. Now, another interesting thing is that if you add these 2 circles, you see B and D occur in that circle. F and G also occur in this circle here. And if you add up all these numbers, let's put it this way, C plus B plus D, that's the numbers in this first left-hand circle, plus G plus F plus H, that's the number, the 3 numbers in the other circle at the bottom. You're going to get 11 plus 11 because they don't cut, which is 22. So these 2 circles, you got 11 there and you got 11 there, they add up to 22. But you already know that these 4 circled ones, they add up to 10. So we can conclude that C plus G, which are the uncircled ones, that must be 12. Because these 2 together, plus those 4, give you 22, 2 11s. So C plus G is 12. Now that's very, very useful because how can you get 12? Right? Which 2 numbers add up to 12? So let's have a look at CG. You got the numbers from 1 to 9. So it could be 3, 9, or 4, 8, or 5, 7. I think those are the only ways you can get 12. Right, from the numbers from 1 to 9 that we have had originally. So 2 of those numbers add up to 12. It can only be 3, 9. You can't have 2, 10 because 10 is not present. The highest number you have is 9. So it's 9 plus 3, 8 plus 4, 7 plus 5. Now, it can't be 3 and 9 because 3 is already taken. It's one of the circles. Right? 3 is one of these circle numbers. 3 is taken, not allowed to repeat. 4 is also taken. So that is out. So CG must be 5, 7. So this must be 5, this must be 7. You could have had 5 here and 7 there. And that you can do, you can work with that separately, and I'm not going to do it. But I'm going to put 5 and 7 here. Actually, it doesn't really matter because whether you got 5 here and 7 here, or if you had 7 and 5, it means you're looking at it from right to left. See, if I had 7 here, then you're looking at this from right to left rather than from left to right. Just think about that. Okay, so this is where we are. I just want to say I've got 2 numbers already. So how do I finish the thing off? Okay, so you've got, what are the numbers that remain? You've got 5, 7, 1, 2, 3, 4, 5, and 7. So the numbers which are left behind, 1, 2, 3, 4, 5, 7. So 6 is not there, and 8 is not there, and 9 is not there. All right, so the remaining numbers, which are these numbers here now, they are 6, 8, and 9. Again, you can try to use a little bit of logic and say that if this is 9, for instance, these two will add up to 11, you see. So these two will add up to 2, and that's not possible. You can't have the 2 numbers from 1, 2, 3, 4 adding up to 2. So the E cannot be 9. If E is 9, then you got a problem. So therefore, the 9 is in the side. I could have had 9 here. I could have had 9 there. Okay. So let's just try this. For instance, if I had a 9 here, let's try here. If I had a 9 here, then this has to be 2. Because these add up to 11. I'll put a 9 question mark. Then this has to be 2. And this is already 5 here. So you got 5 plus 2 is 7. So this will have to be 4. And then in the same way, yeah, this will have to be 4. But now these 2 add up to 4 here. F and H, because this is 7. Yeah, instead of doing all that, that's too complicated. I could have just done it like this. Let me get rid of all this marks that I've made on this thing and focus on this. So suppose this is 9 wasn't here. So 9 is there, and therefore this is 2 here. And we have 5 and 7. So we said if this is 5, 5 plus 2 is 7, that is 4, right? And then you've got 7 here. These 2 add up to 4, so it has to be 1 and 3. So I can put, if this is 3, then that has to be 8. Okay, that's fine. 3 plus 8 is 11. So 3 plus, I could have had 3 and 8 there. And I'm not repeating, that's a nice thing here. 7 plus 3, 1. So that's fine. You got 2, 4, 1, 3. You got 9, 2, 5, and so on. So this gives me a solution. Right? So fill in the 9 numbers. So this is a solution, but I just took a wild guess and I put 5 here. I put the 9 here. I could have put the 9 here. Let's see what happens in that case. If I put the 9 here, and I had a 5 here and 7 here, that this would have been 2, and 2 plus 7 is 9. But then I would have added 2 here again, see? Because these 3 add up to 11. So this is not allowed. You can't put the 9 here. So I could have eliminated that 9, put it there, and that's how we can have the solution. And as you saw, we worked our way through the full solution. So see, pure logic, you can actually solve this problem without guessing. Okay. All right. So that's an interesting problem. And then finally, we now come to the last problem. As usual, I'm going beyond my time. And let's just go to the last problem. Right. So in this case here now, we've got this clock works correctly, but the numbers are missing. So you don't have the, I hope you know what a clock is. A clock with 1, 2, 3 up to 12. Right? In those days before the digital clocks came out, we had all these numbers from 1 to 12. So the 12 was right up there. If the clock is facing in a proper way, then we would have had something like this. The 12 would have been here. 12 and 3 and 6 and 9 and 1 and 2, 4 and 5 and so on, evenly spaced. Right. So that is a clock. Now, none of these numbers are missing yet. And more than that, the clock has been rotated. So you don't have the 12 sitting at the top. So that makes it rather complicated because you don't know where the numbers were originally and it's actually been rotated. And they ask you to find out what is this number, which hour is represented by A. And these are the hours, the thick lines are the hours. Look at this, you'll see there are 12 thick lines. So the 12 hours, and in between you got the minutes. So like for instance now, this is 1 minute past that one. If this was 15, for instance, then this is 16, 17, 18, 19. This is 20. So you have 5 minutes between each pair of hours, right? So the thing is pointing like this now. The question is, what does A represent? Now the actual clue lies here. You see this hour hand. It's pointing exactly to that thing there. In other words, the hour hand has moved through 3 units of the 5. This 5 will represent 1 hour or 60 minutes. Because when it goes from 2 o'clock to 3 o'clock, when the hour hand goes from 2 o'clock to 3 o'clock, you've gone through 60 minutes. So 5 of these small guys represent 60 minutes. So the hour hand has moved through. So one of the small guys represents 12 minutes. So 3 of them would represent 36 minutes. So this hour hand is moved 36 minutes. So in other words, you got 30 here, 35. 35 is here, multiples of 5. So this is where the hour hand is pointing. 36. I'm just thinking it could have been the other way around. Oh, yeah, okay. So the hour hand is pointing to this, but this is not 36. It's only 3 minutes past the hour here. 3 minutes past the whatever this was. But the minute hand would have moved through 36 minutes. Sorry. The hour hand is moving 3 minutes. The minute hand would have moved 36 minutes. So this thing here is a 36. And that's quite possible because this is one more than that. So that point there is at 36. So this here would have been at 35 with the present 7. This number here would have been 7. Because if you had 7 here, that would have gone through 35 minutes. Right? Starting from 12. And you got one more. So it's at 36. So the question is now, so this number here is 7. So therefore this number here would have been 8. So A is 8. So you can actually work out all the numbers 12 to 8 here. But the thing is, this is only one, you see. The clue is that this is only one unit here, and there's 3 here. So the only way you can do that is 3 12 36. So this is 36 minutes past, and this is 1 minute past 7. So this will have to be 1 minute past something. So this will have to be 35, and this has to be 36. Okay, so that's the answer. A is equal to 8. Okay, thank you for staying on till the end. I just want to see who is here. So don't go away. Stop the share now. What happened? Oh, okay. We got quite a few people here. So there